welcome. Here we are, another question. So we did the letter tile possibilities. Let's go ahead and take a look at the, also make sure the stream is working. Popped out the chat, I think. Let's look at the next question here. Is it working? Oh, okay. All right, that's working. I should close this chat. Hello, hello, hello. Oh, okay. All right, that's working. I should close this chat. Very good. Hello, hello, hello. Oh, okay. Good, very good. Also check the mic is not. Yeah, there's no gain. Okay, all right, very good. So we can do this now. So I close the letter tile possibilities, insufficient nodes and root to leave paths. Depending on how long this takes, this might be the last one I do today. So, given the root of a binary tree and an integer limit, delete all insufficient nodes in the tree simultaneously and return the root of the resulting binary tree. A node is insufficient if every root to leaf path intersecting this node has a sum strictly less than limit. Just tried to crack my neck and just got pain instead. Oh, that wasn't good, I think. A leaf is a node with no children. Okay. Oh boy, what a question this is, huh? If you have 5,000 nodes, negative 10, negative 100,000 to 100,000 inclusive, negative a million to a billion, excuse me, negative a billion to a billion inclusive. Not too many submissions and kind of a low acceptance rate. Okay. All right. Given the root of a binary tree and an integer limit, delete all insufficient nodes in the tree simultaneously and return the root of the resulting binary tree. Given the root of a binary tree and an integer limit, delete all insufficient nodes in the tree simultaneously and return the root of the resulting binary tree. Whoa. A node is insufficient if every root to leaf path intersecting this node has a sum strictly less than limit. Whoa. Okay. So the root to leaf path has a sum strictly less than the limit. Oh. Leaf has a node with no children. If every path intersecting this node, whoa. So there's a certain sum that you get to that node, right? That's a constant. And then you have, all the different sums to the, root to leaf paths for that node. And if you add this amount, this target amount to each of those, if all of those are less than the limit, so I think you could take this amount and subtract it from the limit. Or add it to the limit, add it to the limit. It's less than. Yeah, you can add this sum to the limit, whatever it is, and then whatever numbers you get below. So if the limit is, so this example, limit is 1, we'd say 1, 2, so 3, plus 1 is 4, and if everything here is less than 4, subtract from the limit, this 3, yeah. So negative 99 is less than negative 2. It's got to be, it's got to be less than 1. It's got to be, this whole thing summed together is less than 1. It's like negative 200 almost each one. Negative 200 is less than 1 when you add 3 to it. So it's like path sum x plus the other path sum y is less than L, which means that x is less than y minus L, or L minus y. Yeah. So we subtract 3 from 1, we get negative 2, and then this negative 200, well, roughly 200 is less than negative 2. And it's just strict less than. And here we would say it's got to be all paths, right? So you can get the sums of the paths. You want if the least negative path is smaller, meaning the maximum path is still smaller than the limit. So the maximum path here is negative 198. If the maximum of those sums is still less than 1 minus 3, which is negative 2, that means all of them are less than that, in which case this is an insufficient node. If any of them are not less than, though, that means there's at least one path and the node is not insufficient. So we do the same thing here for negative 99, right? The largest path to a node is negative 86. 1 minus 4 is negative 3. Negative 86 is less than negative 4. Or negative 3, excuse me. Yeah, negative 3. So then this is insufficient too. So this gets deleted, this gets deleted. And this one doesn't get deleted though. This one doesn't, because 21 is not less than 21 is not less than 1 minus 4, which is negative 3. So this is not insufficient, the 7. And then this negative, but this negative 9 is insufficient. Negative 99 is insufficient because you get 4 plus 7 is 11. 11, 1 minus 11 is negative 10. Negative 99 is less than negative 10. So the leaf nodes themselves can be removed too. So this one gets removed. These ones all get removed. These get removed. And you're left only really with these ones. So 4, 8, and 9. Here it should be 4, 8, and 9. And then 1, 2, and 3. And then 7 somewhere. And 14. And then all the other ones are gone. Okay, I get it. That makes sense. Yeah, this can be done with the DFS. This is not too bad. This is a relatively high acceptance rate too. Has a low submission rate, but this is not too hard, I think. You just have just a DFS should do the trick. Yeah, I think you could do it in one pass as well. L, just call this limit L, whatever, it's fine. And then there's a current amount, which starts off at 0, which I'll explain what that does shortly. And I'm going to do it this way. Okay. It's possible that the root node gets removed too. Excuse me. Just thinking if the node should be deleted or not. If the root node is deleted. What happens if you delete the root node? Wait a minute. What do we get for the, hold on. Wait a second. What about what if the limit is, I don't know, yeah, -1. Let's do -10. And then let's do -11, 2 and 3. What -2, -3. I don't know, something like this. What does this do? I'm not sure like what I'm supposed to return in these cases. Okay, so -2, -3, and -11. The limit is -10. All the paths, -11 to, so it'll be -13, -14. Both of those are less than -10. And so -11 should be deleted, but -2 and -3 should not be deleted. Ooh, so we don't go to, yeah, so if you delete the root node, then you return a null pointer. Okay. You know, Interesting. Okay. So const val if val is less than limit, turn null pointer. Otherwise, turn the root. Okay, yeah, we don't delete it, then keep it simple, do it this way. So, okay, so we have a tree node, we're gonna have constant amount, we're gonna have constant, actually, we don't need that, we can do it this way. Limit could be like so. And then, okay. So what we would say is we want to get the maximum. So we have f of, so if node, not node, return 0. We're going to say left and right. We'll say constant left is f of node left. Amount will come back to, so we'll say value node amount plus val. F, so it's a left and a right. I'll explain that in a moment, what I'm gonna do there. And then we're gonna say the return result is gonna be, so we're looking for the maximum, the maximum sum of the left and the right. So we're gonna say maximum of left and right. Okay, and that's the value that gets returned. Yes. Okay. So, now what's tricky about this is whether or not, like, how do I delete the nodes? Well, I can decide if the left is sufficient or not. Maybe I could do a pair instead of an int, and it'll tell me whether or not it's sufficient or not. So this is going to return standard make pair of result, and we'll just say it's true. And here we're going to say auto p and p dot first. Really, it's going to be p dot second. Yeah. So this basically will tell me if it's insufficient or not on the left side or right side. Okay, and then we're going to say if if left dot second, then we're going to say node left is a null pointer. Delete left. Right dot second. So if those are insufficient, we're going to delete them. Those nodes. Hopefully this it's just a struct. Maybe implement recursive deletion function. It's kind of funny. Anyway, so node left, node right. So if they're not sufficient, we're going to delete them, right? How do we know if they're sufficient or not? We say, so we're going to create the sum. There's a sum as we go down, as well as a sum that comes up, right? And between the two of them, we have, let's say current amount. Let's do it that way. What we're going to say is constable sufficient is going to be, or insufficient, say. That's going to be when the current amount, if that is, take the limit and subtract that current amount, right? We were saying that before. If this maximum of the left side and right side, which is result, if that is still less than the limit minus current amount, then we say this is insufficient. That boils down to, as mentioned, we're going to get the maximum sum to a leaf of any subpath, right? Any subpath maximum sum. We're going to take the maximum of all those sums. And then we say, okay, those include this current amount, right? Oh, no, not the current amount, plus node val, actually. Oh, no. Yes. No, no. That's confusing. That result is plus node val. I forgot. Yeah. So maximum of all of the paths, and then add the current amount to those paths, so that those are all the paths of this particular root node. And then also, that has to be less than the limit. Sorry, the current root node, but going all the way back up. That current amount. I think I did this wrong. Let's just do amount val. That's confusing. Just do it this way. Keep it simple. Keep it simple. One more time. So it's this result plus val is going to be that's the maximum of any path, and then all the way up to the root is going to be this amount. That's going to be less than the limit. That's so confusing. So it was fine. It was fine to do current amount. All right. It's fine. Jeez. All right. Anyway, that was confusing, but yeah. That's whether or not this node is insufficient, or if it's less than that limit. Those sums are less than the limit. And that'll tell you, so if the left one's insufficient, we delete it, right one's insufficient, we delete it. And then we decide if this one's insufficient, and we also get the left and right amounts. And I think it's that simple. I don't know. Is that it? Seems like that's probably it. It's a pretty straightforward thing. Oh, okay. Get some kind of. Oh, I see. 0, we'll just say it's true. Don't need to delete null pointers. I think that'll make things confusing. Wrong answer, no. Oh no. What happened? What? Really? Well, that's disappointing. Gee. Oh, maybe that's what it is. That could be part of the problem here. So maybe I didn't have it right the first time. Or maybe I No. Oh well, that's fine. Okay. So what? What? What is going on here? What is happening? Oh my goodness. Oh, I did it wrong. Oh, I did it wrong. I see. Ah, true means it's insufficient. Whoops. True means delete. Whoops. This should be false then. Might get a problem here. 1, 2, 3, 4, 5. I'm used to. Yeah, I kind of confused that. Is the idea wrong? I don't think so. I should go this way. Sufficient. Well, no, it's only insufficient. Yeah, it's kind of confusing. Sufficient means it's greater than or equal to the limit. Yeah, I don't know, using double negatives is very confusing. That's, I think, the problem. So just assume everything's sufficient. If it's not sufficient. I think that's what I might confuse myself with. Yeah, this is, I think, what I want. Okay. What's going on here? See the, okay. So, expected 1, -3, 4. It's -1. Okay. So here, -5 gets removed, right? The path to negative is -2 all the way up. 2, 1 is 3. But its paths are also -3. -2. This gets deleted. This gets deleted. 1 has -2 and has 2. So it has 1 path down to the root, so it stays. 1 stays. So 2 disappears. No, -5 disappears. So apparently 2 stays for some reason. 1 stays. -3 and 4. Let's see why 1 stays. -3 stays as well. And 4 stays as well, because all of these have the same 2, 2, and 2 maximal paths. Excuse me. I didn't delete this 2 though. Why not? So the left side is sufficient if there's a current amount coming down, which is 1 and 2, with 3, plus the result, which I think is negative. Oh, that's why. I see. That's the issue. This should be basically negative a billion. Yeah. Negative 1e to the 9th minus 1. More or less. More or less. Oh. Oh, everything goes now if you do it that way. Oh. Whoops. Interesting. I see. Okay. Doesn't really make a lot of sense if you do it. Yeah, I should do it this way. Yeah, I guess you have to do you could do it this way, I think. Here with whether it's sufficient is I see. Result plus node val. Result plus current amount is greater than or equal to the limit. This is the result is just node val for current amount. Result should be 0. Excuse me. Yeah, something like this. Okay. So you gotta handle the leaf nodes separately because this really shouldn't. Doesn't really work properly. Could maybe use an optional, but it doesn't really make sense to use an optional. If you use something too negative, the path calculation gets kind of messed up. Oh, come on. What is this? No, come on, really? What is this? Oh, also, yeah, it still gets messed up. You can't do it this way. Yeah. Okay. Oh, I see. Yeah, run into problems here. Running into problems here. Okay, let's try this way. Okay. Yeah, I've made similar mistakes in the past before. where I didn't realize that the path calculations get more complicated if you have the path calculations become a little more complicated if you're dealing with leaves, because sometimes you can have a node that has a left path and a right path missing, has one path missing. Sometimes you have leaves where they're both missing, and sometimes neither of them are missing. And the problem is that if you don't use like a proper sentinel value for the paths that are missing, then you run into some issues. So that's kind of what was going on here. I'm trying to handle it without making it too complicated, I guess, but also without using a sentinel value. It gets pretty awkward, quite frankly. But now the logic is still correct, but it's just a little more complicated to handle all those kind of variations. Yes. Yeah, that should be fine. Okay, we go for it. I'm gonna go for it. Could be a mistake here, I don't realize, but I'm gonna go for it anyway. Hey, you got there. Very good. Nice. It's a little bit slow, this approach. Let me submit it a few more times. Let me think about how much more time I want to go for here. Maybe do another. Maybe I might want to do another 1 or 2 questions. Yeah, so that's 2. We'll do 3 more submissions. I think I want to use a sentinel value. I think this is not the most efficient way to do this, the fastest way. Let me use an optional. Let's use an optional. Let's do this. Empty optional. Excuse me. Let's do this. Kind of go back to what I had before. Dereference this. So yeah, if they exist, so this is going to be equal to the value, and then if left is going to be so if left at first exists, best to go left at first, dereferenced. And then if right at first exists, best is going to be Something like this. I don't know. I don't know how best to do this. That's confusing. Gee. I mean, this is always an integer, right? Yeah, I think this doesn't make things less complicated. It seems like things are more complicated if I do it this way. It's kind of what we're going for. Yeah. I don't think it's much better. That doesn't seem much better. I think what I had before might have been a little less complicated. Throw it out first. Forgot about that. Yeah, I don't know. I don't know about this. I think the other approach is probably less complicated, quite frankly. Wrong. Oh no. Of course. Output, expected output. So supposed to lose the 3 here, as well as the 1 here. Huh. Okay. Okay. This actually should not be. Result is really the best. This is what best should be. Yeah, it's kind of. Oh boy. Okay. I think I confused this a little bit. There we go. All right, let's go for this one. See if this works too. I think this will be slower than the other one, if it's correct. Oh, it's a lot faster. Okay. Sweet. Okay, it works. Let's try one more time. Really? It's like, I don't know. No, yeah, I was gonna say it shouldn't be much faster. Let's do one more. I don't think it should be that fast. Yeah, no, it's kind of random. It just randomly was a lot faster for some reason. This is definitely pretty complicated here. But that's, I mean, you could use the Sentinel to make things a little bit easier to understand, at least from this perspective. But this is pretty complicated. Yeah, I would say you could do left first, and then say if right first and best, it's so if the right first doesn't exist, then it won't perform the comparison. If left first doesn't exist, say if not best, or if they both exist. So you set it to the left side. If it doesn't exist, we set it to the right side, and we're done. If the right side exists and the left side exists, then take the better of the two. I mean, you could do just left and right. I mean, you could start off with just the best of the two. They don't exist. This is kind of confusing, I have to say. And I'm trying to think of an easy way to do this. Well, you could start off with the left side, and then check if they both exist, then we set it to something. If we still haven't set it to anything, then we set it to the right side. I think that's the way to go. Because if the right side doesn't exist and the left side doesn't exist, then it's fine to set this to the right side, because it'll just be something that doesn't exist. If the left side and right side both exist, then this won't matter and this won't matter. It's get overridden. If only one exists, if it's the left side, this gets set, this gets skipped, this gets skipped, we're done. If it's only the right side, this gets set, this gets skipped, but this will flip and get set to the right side. Yeah, it's kind of complicated though. Like, I don't like how complicated that is. It works, but it's complicated. Hopefully it's faster. I don't know. Not really, no. 1, 2, 3, 4, 5, 6. No. 1, 2, 3, 4, 5, 6. Okay. I think I'm gonna go back to the other solution that I had. That was a little more explicit. Didn't use optionals. All right, let's see this one. Yeah, I think this one's a little bit easier to program. It's not faster. It's just easier to understand what's happening logically. It uses a simple sentinel value here, and then, I mean, this could be an optional too, I guess. But I don't really want to necessarily return optionals if I don't have to. I don't really have to. Yeah, it gets kind of confusing, as I mentioned, with when you're looking at paths. When you're looking at paths, it gets confusing if you try to terminate the recursive condition on empty nodes. It gets, yeah, as I say, it gets confusing. You have paths with side effects. So yeah, okay, great. Yeah, it's a straightforward way of doing it. Not the fastest way, but reasonable way of doing it. Relatively quick to program it. So very cool. All right, I think I'll stop there. Yeah, I spent a little bit of extra time on this. So I spent some time on this one, spent some time on the last one. Well, maybe I'll do one more. Maybe I'll do one more. I like these problems. They are enjoyable. I do enjoy solving these things. Get kind of dopamine hit over here. I like dopamine, man. Who doesn't? So yeah, thank you for watching. If you liked the video, give it a like and follow the stream if you like this sort of thing. And follow for more. And I think, what else do I want to do? I think we'll just do the next question. We'll just jump into the next one. So yeah, thanks for watching. All right.